All right, everybody. So I thought the last video I made would be the last video, the very last, and it turns out I couldn't get everything into the last video. So here's another one where I show you one more topic from the last assignment on scatter plots and correlation. Now, uh, I think it'd be better if I went through real quick everything I've already showed you in order to set the stage for this last thing I'm going to show you. So I have some data, some pair data that it makes sense to go together, at least in the outset, where I'm going to track for 12 athletes, basically their strength versus their speed. Okay, so one variable is going to measure, variables for this need to be measurements, they need to be numbers. What's the maximum weight for which you can do 1 rep of a half squat, and then the time it takes to run a 10-meter sprint. So we're measuring weight and time. Okay, so for time, the greater the time is, the slower the person will be, right? So, all right. And the less the time is to run this 10-meter sprint, the faster they'll be. But those are the variables. Okay. So first thing is, like, you can recognize the scatter plot. Well, let's first look at the data. And in fact, let's look at it in StatCrunch. That's my preferred way to do it. So I get the data in StatCrunch, and if I want to see what the scatter plot looks like, I go to Graph, and I go to Scatter Plot. Okay? X should be the weight, and Y should be the time. And there it is. So I didn't really know how this would go. I don't know if, like, the stronger you are in general, the faster you are, or the stronger you are, maybe you're less limber, or you're heavier, and the slower you are. I didn't know. But it looks like, okay, so time on the vertical axis, weight on the horizontal. As weight gets bigger, time gets smaller. So with the data the way that it is, that would be a negative linear correlation. Okay, weight gets bigger, that's going to the right there, and time gets smaller. That's going down. The line goes down and to the right. Okay, but it's what we call a negative linear correlation. So let's see if we can recognize that first. And that was this. Oh, whoops, done. That was this first one, right? It was definitely not that one, because that's a positive correlation, and it's definitely not this one. It's got to be A or C, but the way the data was given to us, we had time was the Y variable, or the vertical variable, and weight was the horizontal. Okay, so there we go. So it's got to be A. Okay, and then the correlation coefficients, that tells us how strong the correlation is. The closer that this number is to -1, the stronger the correlation is. Now, I say -1 because in this case, that's a negative correlation. It's a linear correlation. I see roughly the pattern of a line going down and to the right. So I think this will be a number fairly close to -1. Probably be like -0.8 or 0.9 or somewhere in there. But this is a very difficult number to calculate by hand if you just had paper and a calculator. So let's look at it. Let's let StatCrunch do the work for us. So I go to Summary Stats and Correlation, and I select both of these, and I hit Compute, and it gives me the correlation coefficient, which is, I thought it'd be fairly close to -1. Turns out it's really, really close to -1. That's why we rely on a number to tell us how strong the correlation is rather than just a picture. We can be misled by pictures, basically, but not as easily by numbers. So the correlation coefficient to 3 decimal places, let's see, I have -0.9697. So that'll be -0.970. Okay, so I got my number. It's -0.970. It says round to 3 decimal places. There's that number that you just saw, rounded to 3 decimal places. Okay, so I got that. And the type of correlation, I would say it's a strong negative correlation, right? It's negative because it's going down and to the right. But it's strong because, you know, R is extremely close to -1. No doubt about that. Okay. All right. Uh, Now next, can we put the correlation into words? I guess when I first had the graph up there, I described it. Um, so as the weight increases, we saw that the time decreased, right? Okay, so let's see if we can find one that's like that. Increases in the maximum weight can be performed. Time doesn't increase, okay. As the maximum weight for which one rep increases, time decrease. Okay, I think it's C. Let me read it again to make sure. As the maximum weight for which one repetition of a half squat can be performed increases, okay, as the weight goes up, that's the way they described it, half squat, whatever, the time to run a 10-meter sprint tends to do. Yeah, that's what I saw, okay? The others just don't line up with what we see in the graph. Okay, now here's the last thing, the new thing that I wanted to show you. So think about what we're doing here. Like I described this when I started it. I said, oh, well, you know, I was like, whoever is doing this research and collecting this data and so on is trying to figure out if these variables are related. Like, does the maximum weight you can lift affect how fast you can run? And this is how they're measuring the data and presenting it to us. But, you know, it's not like we just want to know how this works out for these 12 athletes. You know, when we do statistics, in many cases, we take a sample in order to see, learn, or discover something about a population, okay? So like so many times in recent videos, I said like, well, suppose we want to know something about cats, house cats. Then we might take a sample of 20 cats and we'll study those cats, and then we'll say, well, here's what we believe about the population. Like, and it could be, we want to know the average weight of a house cat. So we take 20 cats and we weigh them, and maybe we average the weights or something like that. And we say, well, this is what we believe the average weight of a house cat to be. So the sample is supposed to say something about the population. So here, if I take 12 athletes and figure out how their strength and speed is related, then ultimately I want to say something that's true about athletes in general, the population of all athletes. In this case, it's soccer players, okay? Now, so when we do that, we can make mistakes. You know, if I say, well, look, there's a strong negative correlation between the numbers that we were dealing with, then what I want to say is I think that that's going to be true, the same thing for all soccer players, right? Whatever the population that these 12 is came from, okay? Where perhaps that's all soccer players or so on. So like I discovered something about the soccer players. I know how their strength and speed is related. Okay, something like that. Okay, but when we do that, we can be wrong. Because, you know, 12 soccer players is just a small fraction of the entire population. So it might be that, you know, these 12 could mislead me. Maybe they're different than the average person in the population or something like that. So my point is, when we have a sample that comes from a population and we make some conclusion about the population from that sample, we could be wrong. All right, the sample could be misleading somehow, okay? It's not that we do our math wrong, it's that we just kind of get unlucky with the sample and it leads us to some false conclusion, all right? No mistakes in math or anything like that. It's just we get unlucky with the sample, all right? Okay, so this last thing will show us how to make judgments about that. Okay. Like, so for example, like this number, the correlation coefficient, is an important number for this. It's pretty close to -1, okay? And that says the correlation is strong. And that says, yeah, it's probably true that the conclusion that I have up here as the maximum weight for which one rep of half squat performed increases, the time to run the 10-meter sprint decreases, okay? The stronger the soccer player is, at least for one rep, as described, the faster the soccer player will be. So that being so close to -1 says that this is probably true for the population. Like this conclusion right here is probably true. But we need to like put a number on that when we say probably. So this number alpha is like the same number alpha that we use for hypothesis testing, okay? If I have an alpha of 0.01, that means that as I make this conclusion with this correlation coefficient, then just by mere chance, I'll be wrong 1 out of 100 times, okay? Because 0.01 is 1 out of 100 times. If this was 0.1, then with these same numbers and same conclusion, I would be wrong drawing that conclusion 1 out of 10 times, okay? So that's what alpha does. Now this is pretty small, so if like whatever I'm about to do will tell me that yes, I can safely draw this conclusion 99 out of 100 times, okay? So now we need to go to this table. See this part here says click here to view the table of Pearson correlation coefficient. Well, this correlation coefficient's full name is the Pearson correlation coefficient. And I want to show you some numbers on it. All right, so see it has n. Now that's the size of our sample. And then it gives us what the correlation coefficient would have to be greater than given an alpha level of 0.05 or 0.01. Okay, so here this is if our say like a sample of 12. Okay, that's how big our sample was this time. Then to safely draw your conclusion and be wrong only 5 out of 100 times, the correlation coefficient would have to be bigger than 0.576. And this number right here says with a sample size of 12, to safely draw your conclusion about the population and only be wrong 1 out of 100 times, R has to be bigger than this number, 0.708. Now we got R to be, what was it, 0.97, okay? That doesn't matter if it's, you can ignore the sign for the purpose of doing this, whatever the number is. But yeah, right there, that 0.97, that's bigger than 0.7, like very clearly. But any number for R bigger than 0.708 would be such that we can safely draw our conclusion and be wrong about it by chance only 1 out of 100 times. So we're in the clear for this one. So we could answer the last part like this. All right, so that critical value is 0.708, okay? And therefore, there is sufficient evidence at the 1% level of significance to conclude that there is a significant linear correlation, okay? All right, now the flip side, if the correlation coefficient, that number right there, ignoring its sign, was not bigger than that, the value from the table, then there wouldn't be significant or sufficient evidence, okay? So that's how we can understand the Pearson correlation coefficient and the level of significance for our conclusion. Anyway, so that will be our last video. Let me know if there are any questions as always.